defects could be of different kinds. You have a metal sheet or a solid sheet. Atoms are arranged in a periodic fashion. It's a crystal. If this periodicity is broken somehow, it's called a defect. A periodicity can be broken in different ways. Instead of a copper atom, you could have a place where that copper is replaced by an iron atom. That's a defect. You can have a vacancy, which means that in the periodic giant array of atoms, one atom goes missing. This is also a defect. You can have an impurity. You could have a periodic arrangement. Just imagine this auditorium in which there is a periodic arrangement of chairs, and few chairs change their position and they go out of sync with the rest. That's also a defect. Suppose one of these rows inside this auditorium gets tilted by a certain angle. That's also a defect. So on this surface we have these two defects, some kind of defects, and they cause the probability density function of the neighboring electrons inside this region to change. This is what we observe with an STM. Here's another example. With an STM, you can have atomic resolution. You can achieve resolutions on the scale of atoms, which means you can actually see atoms. So here on the copper surface, these red blobs represent nickel atoms. Once again imaged by an atomically fine STM tip. And this big blob represents a xenon atom. Xenon has a much bigger atomic number than nickel, so it's a bigger atom here. So with STM you can achieve atomic resolution, and that's why the 1986 Nobel Prize was given to the inventors of STM. Here is a molecule. Not just atoms, but you can also see molecules with an STM. Once again, it's quantum mechanical tunneling that is at the heart of this device. So, quantum mechanical tunneling is not a fictitious figment of our imagination that just exists in fairy tales. It's actually observable in this artificial engineered device, scanning tunneling microscope. So, this molecule is a molecule comprising cesium and iodine atoms, once again on some substrate. These are nickel atoms. These are platinum atoms. The key requirement is that whatever you're going to image has to be conducting, because once electrons tunnel from the tip to the metal surface, they have to flow on the surface of the metal, go out into the circuit and produce a current. So the surface has to be conducting. That's the only key requirement. So you can see atoms. You can actually see wave functions of electrons as well. This is an array of gold atoms. So if I zoom in onto this region is about 11 nanometers by 11 nanometers. So this is an extremely small field of view inside this bigger array of atoms, and I can zoom in further. This box is of size 3.7 nanometers times 3.7 nanometers. And here you can see individual gold atoms in a periodic arrangement, which is the crystal structure of gold imaged by STM. Not only can you find atoms and the structure, you could also find properties. Anything that's related to the electrons can be imaged with an STM. Here you are finding out, you're making a map of the conductance. Conductance means the ability to conduct on a grid of niobium selenide. So these peaks show regions where the conductance is higher. And this is the famous pattern that I alluded at in the previous lecture. These patterns were called quantum corals. So this is a copper substrate, and now an STM tip has been used to pick up atoms. Not only can you image atoms, the movie that I showed you in the previous lecture was actually picking up individual atoms from certain locations, because when the tip is brought closer to the metal, the there is van der Waals interaction and the atom can stick to the tip. And then you change the position of the tip, bring it up, the atom is still stuck to the tip. Then you can move the position of the tip, lower the tip, change the potential, and the atom falls down onto another location. So it's like, so these are atomic forceps. You can use these forceps to pick up atoms from one location on the grid, lift them, bring them to another location, and drop them. And the dropping and picking is done by electric voltages on the tip. Please don't use your mobile phone. You're in a class. So once these atoms are picked up and they're arranged in these nice patterns, so look at this hexagon, look at this whorl, look at this square, this triangle. And once these atoms are arranged in a new fashion, the electrons inside the substrate actually see a different kind of potential. They see a bound potential. And when they see a bound potential, you can have these standing waves, as you see in an infinite well. Here, this effect is all the more evident. You have a standing wave of electrons, or in other words, the probability density function looks like a multi-lobe function, as we've seen in an infinite well. So this is an image of the electronic wave function now. So this is the capability of an STM, a device that is man-made, engineered, which won the Nobel Prize, which helps us talk to atoms at the atomic scale. We're actually talking to atoms at the atomic scale. Now the level of quantum technologies is such that you can manipulate single atoms, you can manipulate single electrons, single photons, and I'm going to give you an example of single electrons today on the blackboard. Now let's switch gears a little bit and let's move to a natural phenomenon which exhibits quantum mechanical tunneling, and which is one of the basic triumphs of quantum mechanics. And that is the phenomenon of radioactivity. Now this phenomenon, excuse me, आपको किस तरह मैं बात करूँ आपसे? अगर आप आ ही गए क्लास में तो तवज्जो चले। So quantum mechanics actually is like a victorious player in all the theories that are aimed at describing nature. And one of the major triumphs of quantum mechanics is the explanation of radioactivity. Now, why is that? Suppose I have a mountain and I have an object here with a certain energy. If this object lies on the top of the mountain, this energy is, say, 100 joules. That corresponds to the height of the mountain. Now there's an observer here. And this observer sees this object. And the object has to come from the other side of the mountain. And this observer has the capability to measure the energy of this object. Suppose the energy of this object is 30 joules, as it is observed on this side. Now, is this classically possible? That you're observing something that is approaching you from the other side of a mountain, it's surmounting a barrier, and the height of the barrier is 100 joules, but the energy of the object that you're observing is just 30 joules. Is this classically permissible?
No.
No, it's not permissible, because this object must have an energy of at least 100 joules so that it can overcome this barrier. If it has 110 joules, it will go up the barrier, it will expend or spend 100 joules of its energy in going up the barrier. It will have a residual energy here, and when it comes down, its kinetic energy goes up, its potential energy goes down, and it recovers all of this energy here. But in order to surmount the barrier, it must have a minimum energy, and that minimum energy is the height of this potential. So we see in quantum mechanically this is possible. Even if this energy is smaller than the potential height, quantum mechanical tunneling can take place. Now this is what's happening in radioactivity. In radioactivity, for example, let's talk about alpha radioactivity. An alpha particle, which is simply a helium nucleus, has some energy. Now, typical energies of alpha particles is around 5 mega electron volts. But these energies are much smaller than the energies of these particles inside the nucleus. For that purpose, let's consider a simple radioactivity model in which uranium, a uranium nucleus, decays. So this parent nucleus goes into a daughter nucleus, which is thorium, and produces an alpha particle. This is the daughter nucleus and this is the particle. Now this particle is coming from inside the nucleus. Of course, I have a bigger nucleus here, the uranium nucleus. Inside the nucleus, there is a combination of 2 protons and 2 neutrons. I'm just drawing a cartoonic representation. So this congregate of protons and neutrons is inside the nucleus and is coming out from the nucleus, and you're observing it. This is what radioactivity is. A nuclear phenomenon. The nucleus is decaying to give you a daughter nucleus and a particle. So the origin of this alpha particle is from inside the nucleus. And this particle, when it's seen outside the nucleus, has an energy 5 mega electron volts. And it will have some energy inside the nucleus. So we would like to see if this particle would remain inside the nucleus, what would its energy be? For that purpose, we need to know what's the potential energy of the alpha particle inside the nucleus. So what happens is that this is a positively charged particle, no doubt. 2 protons, 2 neutrons, and thorium is also, the nucleus is also positively charged. We're talking about nuclei here, not atoms. So both of these are positively charged particles. Now, if this alpha particle is conjoined with the thorium, which means that the uranium has not decayed, then you have 2 positively charged particles interacting with one another, the energy is higher. So it's favorable for the alpha particle, when it comes close to the thorium nucleus, its energy is going up, up. So if I were to make a plot of the potential energy versus the distance from the origin of the nucleus, now instead of x, I'm using r because I have a spherical problem here. I don't want to talk about x, y, and z. I want to talk about r. R is the distance from the origin of the nucleus. So as the thorium nucleus comes closer and closer to the alpha particle, or both of them come closer, the potential energy of the particle goes up because both of them are positively charged particles. If I have a positively charged particle and I'm moving to a positive nucleus, my energy is going up because of electrostatic repulsion. So as R decreases, the potential energy is going up. Okay? The question now is, why can this alpha particle ever exist inside the nucleus in the first place if its potential energy is so high? Or why do nuclei exist? Nuclei contain protons, and these protons are all positively charged particles, So why does the nucleus exist in the first place? If these positively charged particles are all stuck together in a small piece of land which is called the nucleus, they're all positively charged particles. What is keeping them together? Why doesn't the nucleus just fly apart and break away? Because you have positively charged particles. So what keeps the nucleus stable? It's the strong force, the strong nuclear force, one of the four fundamental forces. So as this R decreases, the potential energy goes up. But at a certain distance, which is a very small distance, which is of the size of the nucleus, a new force kicks in, that's called the strong nuclear force, which is attractive, which can attract two protons together, two neutrons together, and a proton with a neutron. So this strong nuclear force, which is attractive in nature, is operable at small distances, and it decreases the potential energy. So this is the potential energy landscape which is relevant to an alpha particle. Inside the nucleus, there is the strong nuclear force, so the alpha particle would like to remain inside the nucleus. Because here, inside the nucleus, this is the, let's call this the radius of the nucleus, an approximate radius of the nucleus, which is of the order of femtometers, 10 to the power 15 meters. So this is the potential energy landscape. If an alpha particle is outside the nucleus, the further it is away from the nucleus, its energy is lower. As it approaches the nucleus, its energy goes high. But once it crosses the threshold of the nuclear boundary, strong nuclear forces kick in, which lower the energy of this particle. Okay, so this is a mnemonic or a candidate potential energy graph for an alpha particle. And of course, this graph is operable for radii. So this is the origin. An alpha particle inside the nucleus has a lower energy because it can have a higher kinetic energy, in other words, because it will have a certain energy, but it's in a lower potential energy regime. Okay, so it can have a higher kinetic energy because the potential energy is low and it can exist inside the nucleus. Now this potential acts like a potential barrier, and this potential has a certain height. We can actually calculate how strong is this potential barrier, and an estimate for this potential barrier is actually given by Coulomb's law. I can have a potential which is 1 over 4 pi epsilon, which is 9 into 10 power 9 Newton meter square per Coulomb square. You've already studied this in your A levels. Then you have two charges, Q1, Q2, and you have R. So this is the magnitude of this potential energy when the alpha particle is at this location Rn here. So this is the potential barrier. Now you have all these values. Q1, which is the charge on an alpha particle, is there are two protons, so it's 2 into 1.6 into 10 to the power minus 19 coulombs. This is the thorium nucleus, because you're looking at the interaction of an alpha particle with the thorium nucleus. The alpha particle is inside the thorium nucleus. That's the second particle. So Q2 is 90, which is the atomic number of thorium. You insert this value. You insert a typical value for the nuclear radius, about say 7 into 10 to the power 15 meters. You plug in these values, plug in the value for this, you are able to find out the energy. Remember, when we talk about energy, we don't have a square here. Okay, because if you took the derivative of this, you would get forces. So if I plug in these values, this energy turns out to be 35 mega electron volts, roughly. Now you have an alpha particle that is still trapped within the nucleus. Its energy is about 5 mega electron volts. Okay? And then you have a high potential barrier which is of a height that is about 6-7 times higher than the energy of the alpha particle. Now, classically, there is no chance this particle can escape the nucleus because it's in what is called an finite well here. If I would like to model this in a simplistic fashion, I would model it in the following way. I have a finite well in which the height of this barrier is 35 mega electron volts, and I have a particle inside which has an energy of a mere 5 mega electron volts. Now this alpha particle will have a certain wave function, and this wave function can decay in this region and be found on the other side. This is called quantum mechanical tunneling, and this is what radioactivity is all about. Even though the energy of this alpha particle is much smaller than the potential barrier, some of its wave function can lead to outside the nucleus. It can go beyond the nucleus because of quantum mechanical tunneling. So there is a finite probability that this particle can escape from the nucleus and become what is called a radioactive particle. So if you were to see radioactivity, which is natural radioactivity, then it's one of the triumphs of quantum mechanics. It actually shows that quantum mechanical tunneling exists. So you can have a low energy particle, a 5 mega electron particle, which is able to overcome a 35 mega electron volt barrier from inside the nucleus. It's issued outside into the external world, into our world, and appears as a low energy particle, even though it has surmounted a big barrier. This is because of quantum mechanical tunneling. Now, if I were to actually show you a table, in fact, when I teach quantum mechanics, I actually derive what's the actual transmission probability here, and we can calculate decay rates as well. But at the level of this course, this is sufficient amount of information. Now what I would like to show you is a table. Any questions up to this point? Yes? It's the size of the nucleus. If the nucleus is, so the question that this gentleman is asking, why are certain nuclei unstable? Why do certain nuclei exhibit radioactivity? Look, it's the size of the nucleus. If the nucleus is larger in size, the strong nuclear forces which are operable at short distances, they cannot overcome the electrostatic repulsion between particles. The attractive forces are operable only on shorter distances. So if you have a bigger and bigger nucleus, these strong nuclear forces will become less effective in holding the nucleus together. And there is the possibility of radioactivity. Most nuclei with bigger atomic numbers are radioactive. So if you look at this table here, I have just listed down a few nuclei, radioactive nuclei, naturally occurring radioactive isotopes. So you have polonium 212, radon 220, two isotopes of radium, and uranium 238, which is the naturally occurring isotopes. And if you look at the energy of the alpha particle that is issued from these different nuclei, if you measure these energies, which can indeed be measured by spectroscopy, then you see that all of these nuclei have energies in roughly the same range. All of them, 5, 6, 7, 8 mega electron volts. So for polonium it's 8.8 mega electron volts, here you have 5.7, 6.3, 5 and so on. So the alpha particles that are ever issued from these nuclei, all of them have roughly the same range of energy. Okay? However, if you look at the mean time to decay, which is also called the half-life, if you look at the half-life of these isotopes, there is an enormous range of scale. There is a range of 10 raised to power 18 orders. This is 0.4 nanoseconds. This is 6.5 billion years, which is half the life of the universe. Of 13.7 billion years is the life of our universe. So look at these range of half-lives. This is a huge range, even though the energies of these alpha particles are roughly the same. So what could be the reason for this? I give you 2-3 minutes to think about this. How is this possible? How do you, as a physicist or as a scientific thinker with some basic knowledge of quantum mechanics, how would you explain this difference? Or could you come up with a reasoning? What determines this mean time to decay? Any ideas? Yes. But the energies are okay, good. But why this huge range? The energies don't exhibit this large range. So this range of energies is about, say, less than 10%. But look at this, 18 orders of magnitude diversity in, yes?
The energy gap between the alpha particle and the potential energy.
The energy difference.
The energy difference between the alpha particle and the potential well or potential energy.
Right, so you're roughly on the right track, yes? So it's the same thing, that roughly the right thing, yes? Excellent, that's actually what I want you to hear. There's an exponential factor here. Let me explain this. So if I would like to calculate with this basic, armed with this arsenal of basic quantum mechanics, if I would like to find out the decay rate, how many decays of the parent nucleus happen per unit time? Okay, so you have a large number of uranium nuclei and you're looking at how many of them decay per unit time. This is what I'm trying to calculate. Or, okay, now what is this going to be equal to? This is going to be equal to the following. Now what's happening here is that you have an alpha particle which is inside a finite well and it's moving with it could be moving with a certain speed. Whenever it reaches the nuclear boundary, it has the capability to go out because of tunneling. Alright? Now a tunneling phenomenon or a decay will happen whenever this alpha particle reaches the boundary. There is a propensity or the probability to tunnel out. There is the likelihood that tunneling will occur with a certain probability. And that probability is given by the tunneling coefficient T that we calculated. The transmissivity. Remember, we calculated the transmissivity. That's the probability that a particle can come out of the barrier, come out of the well. So that's the probability. So the decay per unit time is given by the probability times the number of times this alpha particle can bombard with the nuclear surface. It reaches the nuclear surface. So it depends upon the tunneling probability and the number of collisions of the alpha nucleus with the nuclear surface. How many times, that is, we would like to see how many times, with what frequency does, or how many times does this alpha particle come close to the nuclear surface? Number of collisions per unit time. So it's coming close, it's moving inside the finite well, and it's approaching the nuclear boundary at a certain frequency. So you can have 1 collision per unit time, 2 collisions per unit time. How many times does it come close to the surface? This ratio is the measure of that frequency. And then you multiply this with the tunneling probability. This will give us an estimate of the number of decays per unit time. Now this object here is simply the speed of this alpha particle divided by the diameter of the nucleus. This will tell us the number of collisions per unit time. How fast is it moving, and what distance does it have to cover to come from, to reach the nuclear boundary. From one nuclear boundary to the other, it requires a distance equal to the diameter of the nucleus. Okay? And this is the speed. So I multiply this with the tunneling probability. Now this is a really, really small number. It could be 10 to the power minus 13, minus 15, minus 20, it's a really small probability. The tunneling probabilities are extremely small. But the point is that these tunneling probabilities sensitively depend upon the difference between the energy and the potential barrier. This is the sensitive dependence. And the sensitive dependence is encapsulated by an exponent factor. Remember this factor here. Now this is an exponential factor. If I have to plot this factor versus x, I will get an exponential decay. Which means that I change x by even a little bit. Or, sorry, if I change delta even by a little bit, this graph phenomenally changes. It changes quite a bit. Now this delta depends upon the under root of E minus V naught, or V naught minus E. So if I change E even by a slight bit, then this factor changes by a slight bit. But since this is the argument of an exponential function, which is sensitively dependent upon these factors, there can be a huge change in this tunneling probability. Okay? So this is it all comes out because of the sensitive dependence of the tunneling probability on the difference between the energy and the potential gap. And the half-life is just the inverse of this. The time it requires, the average time it requires for a decay, that's what the half-life is. The average time interval between two decays. So this tunneling probability actually describes why there is a huge diversity in the half-lives. The answer is that the tunneling probability is sensitively dependent on the difference between energy and the potential energy. It's just like even if a butterfly flaps its wings in Sri Lanka, it might bring about a storm in some other region. So that is the level of sensitive dependence. That's why the order of magnitude difference in these half-lives is enormous. 18 orders of magnitude, ranging from nanoseconds, which are these really short-lived nuclei, to these really stable radioactive nuclei like uranium-238. Okay? So it is the mathematical structure of this tunneling probability and its sensitive dependence on E minus V naught under root that determines this huge range of tunneling probability. So even if the energy changes from 5 mega electron volts to 5.1 mega electron volts, it's going to bring about a huge change in T. That's the point. Alright, so let's look at more examples of tunneling. And then I'll talk about a nice electronic example of tunneling as well. In the optical regime, we can also have tunneling, and this is called, let me first show you what does it look like. Suppose I have a prism, a right angle prism, and a photon comes in, or light beam comes in, and it's incident normal to the surface. Now this angle is 90 degrees here. So there is no bending of light. Snell's law states that this beam of light, or this photon, is going to move straight through. However, at this point, the angle of incidence is exactly 45 degrees because it's a right angle prism. Now, at this interface between glass and air, there is what is called the critical angle. At the critical angle, which is sine inverse of the refractive index of this thing, which is about 42 degrees, if the angle of incidence is greater than 42 degrees, then light will not be transmitted. Right? What happens to that beam of light? It's totally internally reflected. So if I had a detector here, and I issued a single photon coming in, then with 100% probability this detector clicks, and if I were to place a detector here, it would never click. Okay? So this is total internal reflection. It holds true in the quantum mechanical regime as well. Any classical behavior, if you don't drastically change the system, it holds true at the quantum scale as well. Snell's law holds, the laws of refraction, reflection hold. However, now let me try to see what's going on. How can I modify this a little bit? Now, a photon here sees a certain potential energy landscape. It sees an interface, which means it sees a potential barrier. And the barrier is so large, it's like an infinite well for this photon, and it's completely reflected. It remains within the well. It doesn't have the chance to escape or evade. I'm using this word evade because it's used and it's important. Now let's look at another arrangement. I have one prism like this, and I have another prism. Which is not joined or conjoined to the first prism, but it's extremely close. Extremely close. So that there is a gap, a really narrow gap here. Okay? Now the beam of light or photons comes in, and you have a detector here that looks at transmission, and you have a detector here that looks at reflection. Now what's going to happen is light cannot penetrate into this air because it's classically forbidden. However, there's a wave function for the photon at the interface. If this barrier is small enough, there is the likelihood of optical tunneling. The photon can optically tunnel into this region. It can cross or surmount the barrier purely due to quantum mechanical reasons. And there will be a finite intensity of light or a finite probability of that single photon reaching this detector, and a certain probability that the photon is going to reach this reflective detector. So you can have optical tunneling, tunneling in the optical regime, tunneling of photons as well. This process, by the way, is called the frustration of total internal reflection. You're frustrating total internal reflection. Now you can make a beam splitter out of this. If you adjust these materials, which means these refractive indices properly, which means you're adjusting the potential energies, and you're adjusting the width of this gap, you can actually make a beam splitter out of this as well. So the probability that this photon is issued here is actually T, capital T, the tunneling probability or the transmissivity that we motivated in the previous lecture. And this probability is going to be R, the reflectivity, which of course depends upon the energy of the photons and the potential energies. Now let's look at another last example of quantum mechanical tunneling. And in this example, I would like to look at the state of the art in controlling a single electron. Okay? Now, the 1952 Nobel Prize was given to the transistor. The transistor, as you know, has revolutionized our way of life. It is a civilizational change, in other words. Without the transistor, we will not have the computer, we will not have information, we will not have information technology, displays. So our life is dependent on what a transistor is. Do you have a question? So a transistor basically has multiple usages and it comes in various kinds. Right from its incarnation in 1952 to 2018, there has been a revolution in how transistors are built, how they're constructed, and so on. And quantum mechanics, as you all know, can never fall behind in this revolution. So it has actually spearheaded the development of transistors. Now, how does a basic transistor work? The basic model of a transistor, let me first explain what it is a MOSFET. It's a metal oxide silicon field effect transistor. I don't remember if it's silicon or semiconducting. Anyway, what's a MOSFET? And then I will explore how quantum mechanics comes in and how tunneling comes in. So a MOSFET is a device which in its simplest forms look like this. You have a material which is semiconducting. We'll have separate lectures on semiconductors, but invoking your knowledge of semiconductors at the A level or FSC, I think this is good enough. We have an N-type semiconductor. And on this N-type semiconductor, we have regions of deposited metal. So this is a metallic region, and this is a metal. One of these is called the source, and this is called the drain. So you have two metal regions, islands, grown inside a semiconductor. Now this semiconductor, of course, it's going to have charge carriers, but very few of them as compared to the metal. And these charge carriers will be all around. These are electrons, because it's an N-type semiconductor. So in an N-type semiconductor, excess electrons that are inside the substrate. Have you all studied semiconductors at this level? Now these are metals, so these have a large concentration of free electrons. That's what make metals conducting. Now what I would like to do, I would like to conduct electrons, I would like to transfer electrons, I would like a charge to flow through this transistor from the source to the drain, as the name implies. So what I would like to do, I would like to connect this to a battery, negatively charged terminal. I would like to connect this to the other end of the battery, positively charged terminal. Now there is a potential difference. Electrons would like to flow from the source to the drain. However, the problem is that you need to have free electrons inside this region as well. You need to have a conducting path for the electrons to go inside this semiconducting region. So even though you've applied a battery, if this battery is not strong enough, no current can flow, and the transistor is in an off state. Because this is a lightly doped semiconductor, only few electrons are available and they cannot provide the necessary flux of charge for current to flow from the source to the drain. So the transistor is in its off stage. Yes? So the electron would like to flow here, like this, from the source to the drain towards the positive terminal of the battery. However, the transistor is still in an off stage. Okay? Remember, quantum computing, off, quantum state 0. You can call it quantum state 0 as well. Now, this transistor has an additional piece of structure built on top of it. In this region, there is an insulator. Okay, so this is my insulator. This is generally a metal oxide. That's why we have the name MOSFET. It's an oxide. It could be, for example, silicon dioxide. It's an insulator. It does not let charges flow across it. And on top of this, we have another metal deposited on top of this. This piece of metal is called the gate. And I can apply a voltage to this gate. What I could do is, I could have this terminal, which is connected to the positive terminal of the battery. I can have a switch that is connected to this gate. Now when this switch is open, nothing special happens, okay, and no conduction takes place. The transistor is in its off stage. Now what I would like to do, I would like to close this switch so that this gate is connected to the positive terminal of the battery and it develops a voltage, the same voltage as of the battery. Okay, so now I would like to close this switch. And then I would like to see what's going to happen to the charge carriers. I apply a voltage Vg, gate voltage, which is positive. So positive charges accumulate on this metal. Now these charges cannot flow onto the semiconductor because here you have an insulator. However, they can apply an electric field. An electric field doesn't require a conductor. An electric field can pass through insulators as well. So this, are you surprised with this fact or is it common sense? Are you surprised? You can have an electric field inside insulator as well. Just remember a capacitor. If you have a positively charged plate and a negatively charged plate, you can have an electric field inside, and here you can have an insulating material. You can have paper, mica, air. The electric field can exist, but charges cannot flow. Currents don't exist. Well, surprisingly, an electric field cannot exist inside a metal. Okay? So you learn this in your next course. An electric field cannot exist inside a metal. This is Gauss's law. However, it does and can and should exist inside an insulator. So even though this positive charge here and the charges cannot flow in and out of this oxide layer, it can exert its influence on the mobile charge carriers that are inside the semiconducting material. And what it does, it attracts all the mobile charge carriers inside the semiconducting material towards itself. So even though charges cannot directly enter or cross this barrier is really important. This has to be non-leaky. This cannot leak charge. It has to be strong enough. This charge can exert an influence on all of the charge carriers inside the semiconductor, and these charges can then be marshaled into this region. They can all congregate here because these are negatively charged electrons inside the n-doped semiconductor. So all of these charges on the heralding call of this sergeant will all marshal together towards this gate. They will all collect together. Now you have a large propensity of a large number of electrons or mobile charge carriers inside this region between the source and the drain. Now we already have a battery connected here. So charges, negative electrons can actually come out of this source, or a channel will exist for conduction to take place from the source to the drain. Electrons will start flowing in this direction because now electrons are available inside this region. We say that a conducting channel has been made. An N-type conducting channel has been made between the source and the drain because of the application of a gate voltage. And the transistor is then said to be in the on state or 1 state. It's on. The transistor has been switched on. The key idea is that you would like to reduce the power requirement of this transistor, which means you would like a large current to flow here. Those charge carriers come from the metal and the semiconductor, but you would like to have a small trigger between on and off. Please pay attention. You need a small trigger, which means you need only a few charges on the gate to actually control the flow of a large number of charge carriers. It's like having river Indus in front of you, and you just have a small switch, a small tributary of the river, a small stream, a really small stream that is controlling the flow of water in river Indus. So you'd like to have only a few electrons inside the gate, which can actually control the flow of millions and billions and trillions of electrons. That's the key. And when you make smaller and smaller and smaller devices, you would like to have this number of electrons reduced so that the power requirements go down. And this insulator can then be thinner because then you have fewer electrons here. When you have thinner substrates, you can pack more and more transistors together, so you can have smaller hard disks as well. So you would like to have fewer electrons here. 50 years ago, you needed 1 million electrons here. 20 years ago, you needed, say, hundreds of thousands of electrons here. 10 years ago, you need thousands of electrons. Now you need only hundreds of electrons at this gate to control the flow of a large number of electrons here. Now, how does quantum mechanical tunneling come in? The question is, can I control the flow of a single electron? Can I have conduction due to a single electron controlled by a single electron at the gate. And we'll take a 10-minute break and we'll discuss this. And we'll see how tunneling is going to help us.